All right, so now we can talk about LU with partial pivoting in general. Okay, so again, the goal is to write P times A. It's like into the product of a lower and upper triangular matrix, where P is a permutation matrix. Then L is lower triangular. And then U is upper triangular. Okay, then P is going to be this product of permutations, which show up. So this is a permutation matrix. And then L is going to be this product of inverses, B1 prime inverse, composed up to Bn minus 1 prime inverse. And then these primed versions, B prime k, is P n minus 1 all the way up to Pk plus 1 Bk Pk plus 1 inverse all the way up to Pn minus 1. And the inverse of a permutation matrix is just its transpose. Pk inverse is equal to Pk transpose. And so some observation. So observe that the permutation matrices Pk have the property that they only permute entries below the main diagonal, right? So Pk and Pk minus 1 permute only entries below the main diagonal. Okay, and in particular what happens to this Bk prime and Bk is that the diagonal 1 stays the same. It's only the entries which are below the diagonal which get permuted. So Bk prime and Bk are the same. With the entries in the kth column sort of switched. Okay, so what I mean by that is that if you have Bk, which is this diagonal of 1s, and then entries minus L k plus 1 comma k, all the way up to minus L n comma k. So this is the kth column, right? Then Bk prime is generally the same thing, except that in the kth column, so you have these entries, but they're permuted. Sort of rearranged, basically. Okay. All right. Okay. So, all right. So the purpose of this is to sort of, negate out those entries below the main diagonal, and then the product L of these things again is going to be a lower triangular matrix, right? All right. So that's sort of just a brief overview of this. So you might ask, well, if you have partial pivoting now, the main difference is that instead of just having A is equal to LU, you have P times A is equal to LU. All right? So you have P times A is equal to LU. You can ask, how do you use such a decomposition to solve a linear equation? Okay, so let's just see how you do that. So solving AX is equal to B. Okay, using a decomposition. PA is equal to LU. Okay, so what you do is that you take AX is equal to B, AX is equal to B, and you multiply on both sides by the permutation matrix P. Okay, so you have P times AX is equal to P times B. All right, now P times A is LU, so that's L times U X is equal to PB. All right, and so I can rewrite this equation into two parts. So again, I look at UX and I call that Y. So I have one equation that says L times Y is equal to P times B. That's one equation. And we have a second equation which says U times X is equal to Y. All right, so together these two, is equivalent to this equation. All right, so now we have a lower triangular matrix times something, some unknown vector is equal to P times B, which I can compute. Okay, so I can solve this using forward substitution. So we can solve for Y using forward substitution. Okay, and then as before, now I have, once I solve for Y, I can use that as the right-hand side for this equation. U times X is equal to Y, and then U is upper triangular, and so I can use sort of backward substitution to solve for this. Okay, so solve for X using backward substitution. Okay, and again, the total cost is dominated by this cubic term, right? So the total cost is sort of approximately 2/3 in cubed flops. There's, if you recall, it's like a quadratic term. N squared, it's like which depends, which has to do with the forward and backward substitutions. But that's sort of small, typically relative to this cost of doing the LU decomposition. Okay, so that's the basic setup for how to do LU with partial pivoting in general, and once you've done this LU with partial pivoting, how you use that to solve a linear system. Okay, so let me stop here for now, and the next thing we're going to do is I'm going to talk to you about what the algorithm is for actually doing, it's like LU with pivoting, okay, with partial pivoting. So let me stop for now.